Hello, my name is Bin Tai, a PhD student from Dalian University of Technology. My report is about the experimental study of plunging solitary waves impacting a vertical cylinder. This report sends 4 parts, and the background will be introduced firstly. Tsunamis can induce destructive power on coastal structures. On the other hand, due to shoaling, waves can evolve into breakers, and thus exert large hydrodynamic loads, notably for plunging breakers. Therefore, in our study, we want to investigate forces of a cylinder induced by the tsunami in the plunging type. Solitary wave theory has been frequently employed in the study of tsunamis due to some properties. There are many studies about solitary wave and its interaction with a cylinder. But regarding to plunging solitary waves impacting a cylinder, a few studies exist. For numerical models, it faces the problems, such as huge calculations and low reliability. For experimental tests, more applied PIV to test the plunging solitary waves impacting a cylinder, but only surface evolution and velocity fields were investigated. Therefore, in our study, wave forces of a cylinder induced by plunging solitary waves are investigated experimentally. This part is our experiment. This experiment conducted in a wave flume, 22 meters long, 45 centimeters wide. The water depth is 20 centimeters. This is a sketch of the experiment setup. Wave gauges are located along the wave flume. A trapezoid bar is placed in the middle of the flume to cause the solitary wave to morph into a plunging breaker. And a cylinder with a diameter of 6 centimeters is placed 5 millimeters above the flat portion of the bar. The top of the cylinder is connected to a force transducer. Prior to and during the wave breaking, surface profiles are captured by a high-speed camera. In wave generation, a third-order solitary wave theory is adopted, and the pedal's trajectory is calculated by MT method. This is comparison between the mild and theoretical surface elevations in time domain. X-axis is the time, y-axis is the surface elevation, and we have 3 incident wave heights. The good agreement confirms that the library waves approximate the theoretical ones well. For cases, we have 3 incident wave heights. The left video shows the case with the maximum wave height. Besides wave height, we know plunging breakers evolve both in space and time. Different breaking phases excite varying forces on structures. Hence, we generated the wave repeatedly and shifted the cylinder to different spatial locations within the breaking region. Each wave height includes 13 cylinders and locations. The part is some results and discussion. This figure shows the mild forces for one case. We can see a drastic oscillation follows the peak value, bothering our analysis. This is because large hydrodynamic forces can excite structural reaction. Conversely, structural reaction will influence the hydrodynamic force. These 2 processes will be included in the mild force. In our experiments, the displacement of the cylinder under wave force is very small. Therefore, the process 2 is ignored. Next, we should extract the hydrodynamic force from the mild forces, and thus a method is needed to eliminate the structural reaction's influence. The structure's reaction is closely related to cylinder's properties, which are expressed by the natural frequency and the damping ratio. Generally, these 2 parameters are constant. However, when surface elevations are included, the mass and its distribution change with respect to time, thus affecting the natural frequency and damping ratio. This is not considered in most experiments. So we conducted different tests at different immersed depths in order to find the relation between natural frequency, damping ratio, and the surface elevations. For hammer tests, based on the equation for motion, we can derive this equation. This is mild force, damping ratio, and the natural frequency is to be confirmed. Then we use the least square method to evaluate the natural frequency and the damping ratio. The left figure shows comparisons between the mild force and the fated force. This figure shows the elevated natural frequencies and damping ratios and different surface elevations. Next step is to find functions to express this. Theoretically, for a structure with distributed mass, the natural frequency is given by this equation. M is the mass. In view of surface elevations, the mass is divided into two parts. Part 1 corresponds to the still water level, and part 2 is contributed by the surface elevation. This equation is written in a simple form. The numerator is the natural frequency in still water, and the denominator includes the surface elevation dependent function. However, the analytical expression of the surface elevation dependent function cannot be given due to the unknown deflection of the tested cylinder. So we use a polynomial function to replace it, and the constants C1, C2, and C3 are determined by the least square method. This figure shows the experimental data under the fitted line. Finally, we get the function for the natural frequency and surface elevation. For the damping ratio, both structural damping and the hydrodynamic damping due to the boundary layer flow contribute to the damping ratio. And it is very difficult to obtain an analytical expression. Therefore, an assumed function similar to the natural frequency is used in an attempt to approximate the relation. This figure shows the experimental data and the fitted line. Although this function responds a crude description, small variations exhibit line sensitivity on the mild forces, and thus this function is adopted. Then we start to extract hydrodynamic forces. This is the relation between the mild force and the hydrodynamic force. Then the central difference method and the functions of the natural frequency and the damping ratio are used. This figure shows the mild force and the corresponding hydrodynamic force for different cases. We can see the mild forces experience dramatic oscillations after reaching their peak values, while the corresponding hydrodynamic forces show essentially no oscillations throughout the environment, indicating that the likely influence of the structural action is removed successfully. With this method, we extract hydrodynamic forces for all cases and plot their maximum values to different breaking phases, seen in this figure. X coordinate means the location of the cylinder that is non-dimensionalized by the breaking point and the impingement point. Y coordinate is non-dimensionalized force. The different color means the different incident wave height. We can see as the propagation of the plunging solitary waves, the maximum hydrodynamic force increases until it reaches its highest value. Then a decay follows. This trend is still followed for the different incident wave heights. In addition, the largest hydrodynamic force for different breaking phases occurs when the plunging jet is curling down, but prior to impinging on the water surface. Then we calculate the ratio between the maximum mass force and the maximum hydrodynamic force, called DAF. DAF can be an assessment of the effect of the structural interaction, and a high DAF indicates a drastic structural response that is harmful to structural safety. In this figure, we can see DF exhibits a similar relation to the hydrodynamic force, indicating that the strongest hydrodynamic force has the maximum DF and induces the strongest mild force as well. Finally, we summarize two main conclusions. The first is a method based on the equation of motion is proposed to extract hydrodynamic forces, and the surface elevation's influence on properties of the cylinder is considered. The second is the maximum mild forces, hydrodynamic forces, on DF occur approximately at the same breaking phase, that is when the plunging jet has cooled down, but prior to its impingement on the water surface. Thank you.